I have a question. You have a generator or transmitter connected to the coaxial cable. The coaxial cable is wired to the coil, whatever. The frequency could be any frequency, 150 megahertz or 150 kilohertz. Instead of having a resistor at the end of it that's 50 ohms, so it would dissipate as a heat, you're closing it. What's going to happen to the signal there?
Okay, you said instead of having a 50 ohm resistor that absorbs all the energy as the heat, and then you said something else and I missed that, so repeat the second half of that sentence, Wes.
You're shorting the end.
Okay, of all the possible resistors you can put on the end, everything from a short circuit, let's call it 0 ohms, up to a complete open circuit, it's called infinity. So you get a whole continuous range of resistors, from short to open. And you also have a whole continuous range of reactors you can put up there. Everything from negative infinity, which is capacitive, to positive infinity, which is inductive. All of those are possible. Okay, let's just talk about resistors at first. 50 ohms, all the energy gets absorbed. If I make the resistor 49 ohms on a 50 ohm cable, it's lower than the characteristic impedance of the cable.
We're going to repeat that few times. The characteristic impedance of the cable.
The characteristic impedance of the cable. The characteristic impedance of the cable.
The characteristic impedance of the cable. If the resistor that is connected at the end of the coaxial cable is, let's say, 49 ohms, that is lower than characteristic impedance of the cable, we're going to create a reflected wave back to the transmitter, and standing wave as well.
You're going to get some amount of reflection, a very calculatable amount of reflection.
Right. I'm gonna show you right now the coaxial cable, only the inner wire with a piece of the insulation on it, which shows here on the right hand side, right on the top, the forward wave, and at the bottom, reflected wave. At the left upper corner you can see the link to www.hamuniverse.com, and you can read more about it. So whether we short coaxial cable at the end or we short 300 ohm ladder line, which is our old flat cable from the TV, we're gonna have a similar behavior, and yet it will lead us to all of the bifilar coils that we play with. So depends on the shape of the transmission line. We have different impedance, which would be the resistance to the particular frequency of wave, and that will have a properties of capacitive and inductive reactance. Coaxial cable is made usually as 50 or 75 ohm of impedance. Flat transmission line could also be called twin lead.
And that is, you know that 50 divided by 49 is a 1.1 or whatever is the standing wave ratio. And that you can then calculate exactly how much reflection you're going to get. And something else. A time domain reflectometer will tell you this. Any amount of resistance smaller than 50 ohms on a 50 ohm cable is going to give you 180 degrees of phase shift on reflection. So lower in ohms, 180 degrees of phase shift. Higher in ohms, no phase shift, but still reflection. So as you go to higher and higher number of ohms, you get more and more reflection. As you go to infinity, every bit of the signal you send down the cable reflects back to you. I'm assuming you're at a frequency that's not so high where the little bit of semiconductor at the end starts acting like an antenna. 10 gigs, you're going to get that effect. But at normal HF frequencies, higher than 50 ohms reflection, the higher the number of ohms, the more the amount of reflection. And you can get 100% reflection from an open circuit. You can get 100% reflection with 180 degrees phase shift on a short circuit. Your TDR, by looking at the waveform on your TDR, and you look at the echo pulse, is it positive going or negative going, tells you is the impedance at the end higher or lower, and the wave shape tells you whether or not there's any capacitance there. So you got a lot of information on that oscilloscope screen of a time domain reflectometer that uses this phenomenon. So I know that this is the beginning of a question, and give us the rest of the question, Wes.
Inductive character, capacitive character, when it's happening, when I'm increasing the frequency over the frequency of resonance of the coax.
Okay, this is getting very close to one of my favorite puzzles of my 30 or so physics puzzles. And when I give this one to electrical engineers, a high percentage of them have trouble with it. And here's the way I word it. I've got a sealed box at the end of the cable. It's got a good connector going into a sealed box. And inside the box is a thoroughly shielded, perfect variable capacitor. So in my frequency of operation of my signal generator, I've carefully adjusted that capacitor so it has exactly 50 ohms of capacitor reactance. So I got a 50 ohm capacitor at the end of a 50 ohm cable, and I asked each of these electronic engineers, am I going to get any standing wave ratio, or am I going to get any reflection of signal? Will any of these signal be reflected back to the transmitter? At least 3/4 of them will say, no, you've got a 50 ohm load at the end of a 50 ohm cable. They make the mistake of thinking a 50 ohm capacitor reactance is a good load on the end of a 50 ohm cable. The next question I asked them is that if it was a 50 ohm resistor, you know what's going to happen. All the signal you send down there gets absorbed by the 50 ohm dummy load, and none of it comes back. It gets turned into heat. Okay. I then ask them, if a 50 ohm capacitor is a perfect load, where does the energy go? And then you get a funny look on their face. Because they eventually realize, whoa, you cannot continuously put energy of any kind into a pure capacitive reactance. You can put an amount of energy in there once. I mean, if the capacitor has got, let me pick a number, 50 picofarad, and I put 50 volts on it, 1/2 CV squared, I can calculate the number of joules of stored energy in the capacitor as a one-time event. But if I'm putting a 50 ohm dummy load out there, and I run the transmitter for a year, that dummy load of 50 ohms will continuously absorb that energy for a year and turn it into heat. That capacitor at the end, maybe you could put some energy in there for a fraction of a second, but where's the energy going to go? A pure reactance is lossless. It cannot continuously absorb energy. So by definition, you put a pure reactance, capacitor, inductor, whichever, it has to reflect all of the energy you sent into it. It's going to create a phase shift in the process of doing it. It's going to change the wave shape you get on your time domain reflectometer in a very characteristic manner. That once you learn to do pattern recognition, you'll say, yeah, I know what that is. That's a capacitive load at the end of that cable. And by how much it gives you this effect, you can tell exactly how many picofarads of capacitance it's got. So a capacitor must reflect. If now you put a capacitor in series with a resistor, you're still going to get a phase shift, you're still going to get a reflection, and you're going to get a very predictable amount of reflection. I can tell you the equation that gives you the exact amount of reflection. But once you know the real impedance, and every real impedance is a resistive component and a reactive component. The resistive component is anything from 0 to infinity. The reactive component is anything from minus infinity to plus infinity. And you represent that as, a complex number, R plus JX they call it. So the real impedance, if it's a series reactor plus resistor, is called a R plus JX. And if you put the two in parallel, there's a similar formula where you do it in conductance instead of resistance. But still, once you represent it as a complex number, a real component plus a reactive component, the real component has nothing but a magnitude above 0. Although, wait a minute now, you could have a negative resistance. There is something, you can create a negative resistance electronically. But you've got a resistive component and then a J, meaning the square root of 1 in front of the reactive component. And once you've got that representation, you plug it into a particular equation. That equation will tell you exactly what percentage of that energy is going to reflect back to you. And that equation will tell you exactly what phase angle is going to reflect. So As crazy as it sounds, it's a very deterministic situation. And you could say the whole philosophy of a vector network analyzer, the whole philosophy of the Smith chart, the whole philosophy of polar representation of RF energy